Hello my dears, very good morning to all. So what we studied yesterday, we discussed about some types of torque, right? Some types of torque in the permanent magnet, torque in the measuring instrument, right? Deflecting torque, controlling torque and damping torque, etc. And we did some problem regarding that error, right? That error also we did. So today we are going to move to an important session in measurements, which is nothing but permanent magnetic moving coil instrument. Short form, it is called PMMC, permanent magnetic moving coil instruments. So these instruments are based on D'Arsenoval principle. D'Arsenoval principle. So what is mean by D'Arsenoval means, if a current carrying coil is situating in a magnetic field, that coil will experience a force, and due to that coil start moving or start rotating. So that rotation can be utilized as a meter or utilized by connecting to a pointer, and the amount of deflection can be, or indirectly the amount of current can be, we can calculate. So that is the basic principle of a D'Arsenoval meter. So a current carrying coil placed in a magnetic field will experience a force, and due to that force it will rotate, or it will turn, or it will move simply. So that is the meaning of a D'Arsenoval principle. So in PMMC instrument, here we are using two permanent magnets made up of alnico. I already explained that alnico is the best material for making permanent magnet. So okay, this is the permanent magnet material alnico, and there will be an aluminum frame. It's a rectangular shaped aluminum frame will be there. Over that aluminum frame we wound coils which having n number of turns, my dears. And there will be a spindle, in which the spindle is connected to the aluminum frame, so that the spindle along with that aluminum frame will be rotating. Okay, that will movement. So in that two ends of the spindle, we connected two springs, and each springs are oppositely coiled. These are what? Spiral spring, right? Spiral in structure. So each spiral springs are oppositely coiled, which means if one turns to tight form, other turn to loosen. If one started tighten, other started loosen. Okay, so then only that controlling effect will be there. That is the reason for this oppositely coiled two springs are used. And again on the top of the spindle, we are using jewel bearings. Simply bearing, my dear. Bearing is used for, the spindle is moving, right? The spindle is rotating like this. So this rotating can be as much as smooth, as possible as smooth, in order to reduce this frictional error. So we are using bearings, and this bearing is made up of sapphire. Sapphire is very costly, Sapphire is very costly. So that sapphire bearings are used here. And the two sides are connected with the bearing, so that the spindle can be easily moved without any friction. And the movement is connected to the pointer, and it is connected to a scale. So this is the general constructional details of the PMMC, and let's see how it will work. And similarly, see, I already told you, this is the based on the D'Arsenoval principle. So which is nothing but, see, this end is act as the current incoming point to the meter. This spring carries the incoming current, or the current which is to be measured, okay, or the working current. And through that it will move here, it will connected to the coils, and it will circulate like this fully, and after that it reaches the second coil, and after it will go to the, means it will complete its path. See, one coil it is connected, so this is the connecting end, come here, after all the turns it covers, after the passing through this spring it come outside. So across this you can apply the DC supply, right? Across this you can apply the measurement quantity, whether it may be voltage, whether it may be current, or anything you can apply. So this is the current direction. So what happened, when this current is flowing through this coil, when the current is flowing through this coil, this is the rectangular shape. This is a rectangular shape aluminum frame. So that what happened, my dears, there will be one force which is acting in this side, which tend to rotate into the board, and one force which is acting in this side, which tend to move the cylindrical, that rectangular coil outward from the board. So that ineffectively one torque is acting like this, another torque is acting like this, so that it will rotate. And the force acting on this surface, now this horizontal surface, it is 0. So there will not be any torque acting on the horizontal surface. Only vertical surfaces of the rectangular coil will experience a force, and that too in opposite in nature. So equal and opposite forces forms a coupled, right? Coupled, force coupled, it will generate, so it will rotate. And see, the nature of this face of the permanent magnet is in the form of a horseshoe, right? Horseshoe, in the form of a horseshoe. Why? Means in order to provide a radial flux. In order to provide the radial flux, which means the flux has to focus like this. That means there will be less number of leakage flux from the permanent magnet, of course, so that it will be very, very accurate and very high sensitive meter also. So for that we are making a radial, a horseshoe structure on the surface of this pole shoe or pole face, so that the radial flux will be there. Means the flux will be maximum concentrated, or maximum flux density will be there. Maximum flux density will be faced by the rectangular coil. So for that we are making the permanent magnet, the moving, in the PMMC, we are making this permanent magnet in the form of a horseshoe on the pole surface or the pole faces. And that's all about the construction and working. And let's see the torque equation. And why these coils are oppositely coiled means, see, if one is start rotating means one coil start tightening, at the same time other coil start loosening, then only that working will be there, na? If both the coils are tightening means it will not work. So you can imagine, like, okay, both of the coils are oppositely coiled coils are there, but one is tightening means other will be loosening, then only it will be perfectly work. Okay, so that's all about the working, and it will directly give you the value to be measured. Okay, and the important session here, this is the construction side. The points very important: DR Sonobil, Alnico, sapphire bearings, horseshoe arrangement. These are the important point in order to note for the examination point of view. Next we have to see the torque equation. We have the developed torque equation like TD is equal to NABI Newton meter, where N is equal to number of turns of the coil and A is equal to area of cross section of coil in meter square, and B is the flux density. You know the unit, right? Weber per meter square, and I be the current, simply current, I be the current. So this is the torque equation. So under steady state condition, my dear, I already told you that when TD increases, TC also increases. TC also increases in equal and opposite manner, so that TD and TC under steady state condition, TD and TC are same. So that TC, it is a spring control, right? For spring control, I already told you the TC will be directly proportional to K theta. Am I right? For TC, for spring control, TC proportional to what, my dear? K theta. Am I correct? And TD is equal to NABA, right? not proportional, directly you can say Tc equal to k theta. Tc proportional to theta. If you remove that proportionality concept, it will become Tc equal to k theta. So, and Td is equal to, what is the equation for Td? I already found you. Td equal to NABA. So I can write like NABA equal to k theta, or simply theta proportional to I. Am I correct, my dear? Because N is a constant, A is a constant, B is a constant, K is a constant. So only term is not constant is theta proportional to I. So we can say that there will be a deflection which is directly proportional to I. Theta is nothing but, my dear, the deflection. Deflecting angle directly proportional to current. Is it clear? Deflecting angle directly proportional to current. If something is directly proportional to current, means we can say that it is a that type, or that is a, can I rub this? If something is directly proportional to current or something is, we can say that it is a linear scale device. It is a linear scale device because theta proportional to I. Theta proportional to I means it is a linear scale device. And we can use or use it in DC only. Use it in DC only. Why? Because, see, I will say one thing. Suppose if we are passing AC to the permanent, it's a very important question, my dear. Very important from this session is this question. If we passing an AC to a permanent magnet moving coil instrument, PMMC, what happened? Since the torque, the deflecting angle is directly proportional to I only. So for positive half cycle, what will be? Theta proportional to plus I, correct? Plus I. So the deflection will be in positive direction. It will tend to move, it is in positive direction. And for negative half cycle, theta will be minus I, because it's negative half cycle. So deflection will be in reverse direction. If the frequency is very high, my dear, suppose it is in 50 hertz frequency, suppose you imagine our supply frequency is 50 hertz now, which means a cycle can be completed in 20 milliseconds. 20 millisecond a cycle will be completed. 20 millisecond a cycle will be completed. This much fast will be the cycle. This much fast will be the cycle. So what happened? A half cycle will be completed in 10 millisecond. A half cycle will be completed in 10 millisecond. So in 10 millisecond, the positive half cycle over. So what happened? The meter will try to move in positive direction, but next 10 millisecond will come fast. So again it will deflect towards reverse, which means reverse. Again it is tend to move in positive direction, again reverse. Finally, my dears, this moving coil instrument, the meter won't move because it is having certain inertia. Whenever it start moving, next half cycle is come. Whenever it start moving, next half cycle is come. It can't move. So under a very high frequency, say 50 hertz supply, more than 50 hertz supply, the meter doesn't move because it can't respond to that type or that high frequency wave. It can't respond because it has a certain inertia, right? So it can't respond. So that is the case, or that is the condition when we pass to a high frequency AC. But what happened when we are passing a low frequency, if we say 2 hertz? Suppose a 2 hertz AC we are passing, what happened? The meter will give, or meter will have the enough time, because one cycle will be covered in 1/2 seconds. 0.5 second is not that much small, right? Not that much small. 0.5 second, half cycle will complete. Okay, one cycle will complete. So 0.25 second will be for one half cycle. Half cycle. So what happened, my dears? So this 0.25 second is not that much small. It is a quantity, right? So for positive half cycle, the meter will move like this. For negative cycle, it will come back. Positive, it will move. Negative, it will come. Positive, it will move. Which means the pointer start oscillating. The pointer start oscillation. And the number of oscillation is simply nothing but the frequency. Number of oscillation is simply nothing but its number of oscillation per second will give you the frequency. Exactly 2 Hertz, you will get the frequency from that movement of the pointer. So, as a conclusion, for high frequency AC waveform, we can't, the needle will not deflect. There may be options like this. When we are passing AC to a PMMC, what happened? PMMC will burn, it will not read, it will read to full value, none of the above. The answer is, it will not read. The answer is, my dears, it will not read. Okay? Is it clear, my dears? So this is called the DC measurements, DC measuring device. DC measuring device. And advantages. 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 First one, high strength permanent magnet. That means we are using here the permanent magnet, no? At 2 sides or 2 poles we are using permanent magnet. It's not having very high flux density. It's not having very high because it's a permanent magnet. A good magnetic material, alnico is a very good magnetic material. So what is the advantage of using that means there will be some magnetic field will be there called stray magnetic field. Stray magnetic field. Stray magnetic field is nothing but, my dear, this is the device. This device is connected by using so many wires, right, in the circuit. So that wires carry certain amount of currents, right? So due to that currents, there will be some magnetic field around the devices, around the device or our PMMC, around our PMMC. So it may affect the reading of the meter. So stray magnetic field is nothing but, my dears, the magnetic field produced by the wiring or the magnetic field produced by the neighboring connection or the magnetic field produced by the neighboring conductors, that all comes under the category of stray magnetic field. That is very feeble in nature. That is very, very feeble in nature. Since our PMMC instrument having a very good, very strong permanent magnet in it, inbuilt in it, the stray magnetic field will not affect, because it having its own very powerful magnetic field, then that stray magnetic field, it will not affect the PMMC. So no stray magnetic effect will not be there due to high strength of permanent magnet. That's very, very important advantage of PMMC. And next advantage is that it having high torque to weight ratio. High torque to weight ratio. Torque to weight ratio. If the torque to weight ratio is very high means, for a small, very, very small machine having a very high torque, that means torque is high and this is low. For very low weight of the machine, we can produce a very high torque means it having high sensitivity. It having very high sensitivity. So the machine having very high sensitivity and it having very high torque to weight ratio. Since the torque to weight ratio is very high, the power consumption will be very less. The power consumption will be very less. So what are the advantages here means? It having high strength of permanent magnet, so that stray magnetic field will not be there, and it having very high torque to weight ratio. If torque to weight ratio is good for good device, torque to weight ratio should be high. For a good device, for a very sensitive device, very high sensitive, we need a very high sensitive device. That means even for a small changing the parameter that we fed to the machine or to the device, it will deflect or it will respond at least. So that is the meaning of a high sensitivity. So this is a very high sensitive device, which means its having torque to weight ratio will be very high, very high, so that the power consumption will be very less. So clear? Next, errors. Of course there will be error due to temperature change. Temperature change may affect the overall reading, because they are inside the meter. We are using conductors, right? So the resistance of the conductor is changing with respect to the temperature. It is increasing when increasing temperature. So what happens, we have to use a compensating resistor. Made up of manganese is connected in series with the meter. So a temperature change will be there, so that it may affect the reading. So we are using compensating resistor, which is made up of manganese, my dear, which is made up of manganese, and which is connected in series with the meter, so that there will not be that much change due to temperature will happen, because it having almost this manganese, no, my dears, it having 0 temperature coefficient of resistance. It having almost a 0 temperature coefficient of resistor, so it will definitely opposes the changing resistance with respect to the temperature variation. So our readings will be that much accurate. And this manganese, my dear, which is made up of 86% copper plus 12% nickel, 12% I think, yes, manganese, sorry, 12% manganese and 2% nickel. So this is the combination of this manganese. Which will not be asked for, just for the understanding. Okay, the percentage and all you won't need to remember. You just need to remember this name. Manganese is used in the PMMC. And another type of error may be due to the aging. It is quite natural, right? So by the time, when time passes, what happened? The spring, the continuously coiling and uncoiling process will be there. So over years and years, what happened? The tension in the strings, or the tension in the springs start decreasing. If the tension starts decreasing, means the spring, it is designed for certain range, right? So that range will vary. Then even a small current will lead to a small coiling, I mean a very big coiling or very big uncoiling, depending upon the meter. So the aging is, we can't do anything. We can't compensate for aging, right? We can't compensate for aging and all. And next is frictional error, ideas. Frictional error. You know this, right? Because both the sides are connected with the bearings. So both sides are connected, right? It's a moving part, right? So there will be, of course, friction. So in order to reduce the friction, we are using a very good quality bearings. So in PMMC, we are using sapphire bearings, correct? We are using sapphire bearings, so that maximum error can be minimized due to the the presence of that frictionless movement of the sapphire bearings, So that's all about the advantage, my dear. That's all about the advantages. Okay. And of course, the aging of aging of spring as well as aging of permanent magnet will be there, right? Both will have age, right? Both have aging problem. That's not only the springs but also the permanent magnet. So the permanent magnets are made by once a strong magnetic field applied and permanently it is magnetized. That is the material alnico. But what happens by the time pass? What happened? The strength of the permanent magnet will start to reduce. So that again error will be happen due to the changing the strength of the flux density of the permanent magnet. Okay, my dears, is it clear? So that's all about the working, and this is just you have to remember these terms. This torque by weight ratio, high sensitivity is very high, no? That terms you have to remember. Not that much deeper we want. Okay. So that's all about the PMMC. Okay, my dear, so let's do a problem. A PMMC instrument, in a PMMC instrument, the strength of magnetic field, or simply the strength of magnet, reduced by 0.05 percentage per degree Celsius rise in temperature and due to rise in and spring weak by 0.03 percentage per degree Celsius for a temperature variation of full stop for a temperature variation of 20 degrees Celsius, the effect of the readings of the instrument, Okay, how can we solve, my dears? Okay, in a PMMC instrument, the strength of magnetic field reduced by 0.05 percentage per degree Celsius rise, and the spring weak by 0.03 degree Celsius, 0.03 percentage per degree Celsius. For a temperature variation of 20 degree Celsius, the effect of the reading of the instrument will be. Listen, my dear. So the magnetic field reduced by reduction in B will be what? Equal to 0.05 percentage for per degree Celsius. Now per degree Celsius. For 20 degrees Celsius it will be 20 that much percentage. So it will be equal to what, my dear? 5 by 100 with 25, so it will be 1%. So 1% reduction 1% reduction in B will happen, right? Okay, the strength reduced by Hana, so it will be 1% reduction. And the spring weak by, so reduction in spring strength. Reduction in spring strength will be what? 0.03% per degree Celsius means. For 20 degrees Celsius it will be, my dear, 0.03 into 20%. So it will become what? 0.6% decrease, right? Decrease. So what happened, my dears? Listen. If there is a reduction in B means, what happened? There will be, of course, the deflecting torque. See, we have the equation TD equal to NABI. So what are the fact connecting means? B is one fact, correct? So if B reduces means TD also reduces proportionally, because TD proportional to B, correct? TD proportional to B, my dears. So definitely this will reduce. So if B reduces by 1% means TD also reduced by 1% from case 1. This is case 1, my dear. Case 1, and this is case 2. It's case 2. And reduction in spring strength, my dears. Reduction in spring strength means if the spring is reduced, strength will be reduced means the deflecting torque. What happened to the deflecting torque? It affects the controlling torque, right? At a steady state, deflection torque and controlling torque are equal, correct? So if the reduction in spring strength happen, the spring is loosening means what happened? The deflecting torque will be very much higher, correct? If it is very tight means, my dears, if it is very tight means the deflecting torque will be a super good condition. If it is very loose means the deflection torque will be very high. So if the reduction in spring strength 0.6 reduced means that much increment in deflecting torque will be there. Is it clear? Because we have TD will be equal to, my dears, TC. TD will be equal to what? TC. So TD, or I can say that TC will be equal to what? Proportional to B. Or TD proportional, or simply see TD equal to TC. You just take that. TD equal to TC. If the spring strength reduces means we can say like TD will be equal to K into TC is nothing but, my dears, K theta. If this K will affect here, my dears, that is the main thing. K is nothing but spring constant. It is depending upon the nature of the spring. So if the spring constants, the reduction in spring constant means the spring constant will be reduced means deflecting torque will be increased. Deflecting this K value start increasing, not decreasing. K value will increase. Spring constant means the K value is for a very tightened spring, the K value will be very less. For a very loose spring, the K value will be very high. That means if the spring, or you can think logically, if the spring is very much tight means the deflectant will be, the deflecting torque will be produced by opposing the tightening. Opposing the tightening only the deflection will be produced. If the spring is very loose means the deflection will be very high. The deflection will be very smooth and very fast. That will lead to an error in the reading. So what happened if the spring strength is reduced by 0.6% means it is indirectly mean that TD increases by 0.6%. TD increases by 0.6%. So effective change in TD will be what, my dears? One, it is reduced by 1%. In another, it is increased by 0.6%. So effective value will be 1 minus 0.6 reduces, right? So it will be 0.4% reduction. In TD, there will be 0.4% reduction will happen. In TD, there will be 0.4% of reduction will be happen. Is it clear, my dears? Is it clear to you? Is it clear to you? Okay. Is it clear, my dears? Okay. Next, MI instruments. MI means, my dear, moving iron. Moving iron instruments. Just to draw the schematic diagram, it will be very easy then. And one more thing, my dears, the controlling torque in the previous case in PMMC, the controlling torque provided by that spring itself, right? The spring control we are used. And what for the damping? What for the damping purpose? In the PMMC instrument, the damping torque is provided by the which type of damping torque that we provided there is what? Eddy current damping. Eddy current damping, you have to note that, because the aluminum frame now, it is moved between the magnetic field. So whenever that rotation happens, it is suppresses by itself by producing some eddy current in it. So eddy current damping will be there in the what? PMMC instrument, that you have to note. Okay. I forgot to say. Supply. Listen, my dear. Draw this figure. Draw this figure. It's just a schematic figure, my dears. In the examination, we will not expect this type of construction and construction type. Construction regarding the questions regarding construction and all, it will not ask. So we don't need to focus on more on this construction and all. Just need just a picture we have in our mind. Okay. So see, Mi means moving iron. As the name indicates, there will be a movement of iron will be there. There will be a movement of iron. That is called the soft iron disk. This is about to move by this direction. This is about to move like this. Okay. This movement is converted into the movement of the pointer. This movement is converted into the movement of the pointer by some arrangements. Okay. And here we are using the air friction damping. Here we are using the air friction damping. And why we are using, I will tell. Okay. And here you see there will be a supply and there will be iron core. A soft iron core will be there, and the surface of the iron core a winding will be there, oppositely winded, right? This is for incoming current and this is for the current moving outward. Okay, so this is the supply. So this supply in which we have to apply the unknown current, right? The unknown current is applied through the supply. So what happened, there will be a flow of current, so that this is magnetized. There will be a magnetic field around the soft iron core, right? There will be a magnetic field around the soft iron core. So due to that what happened, this is soft iron disk, my dear. So what happened, if the flux is very high, means this will be attracted towards the soft iron core. This will be attracted towards the soft iron core. If the flux is very weak, means it will start slowly this discharge, start discharge. Okay, so what happened, this is a soft iron core. When it is magnetized, when strength increases, the magnetic strength increases, the more and more it will attract towards the soft iron core. This attraction, my dear, can be converted into the movement of the pointer. So the movement can be noted. And here we are not using eddy current. Here we are not using eddy current because there will not be, see my dear, there will not be any very strong magnetic field is not here in order to produce such type of a good eddy current damping. Here the magnetic field is very feeble. The magnetic field is very feeble, and also the magnetic field is continuously changing. The magnetic field is continuously changing with respect to the AC because we are applying AC supply. So that eddy current damping now, it will not work here. That will not work here. One, the magnetic field is very feeble here, and also compared to the Pmmc, and next one is that there will be alternate changing the polarity of magnetic field, so that eddy current damp will not work there. So a perfect damping for this Mi type instrument is that air friction damping. A perfect damping for Mi type instrument. For MC type instrument, the damping was eddy current damping. For Mi type instrument, the damping will be what? Air friction damping. The damping will be air friction damping. Is it clear? Is it clear? And let's see the torque equation. You just need to by heart this equation. No need to derive and find. It is half I square into dl by d theta, where dl by d theta is nothing but the changing or the incremental inductance with respect to the deflection. This is nothing but incremental inductance, or simply changing incremental inductance with respect to what is called this deflected angle. Deflecting angle. Okay, and of course I know the value, you know the value of I. What is I means? It is a current which is passed to flow, right? Which is passing through the iron core, or the measurement quantity here, it is I. So this is TD, and we are using the controlling torque again by the spring control. So definitely TC will be what, my dear? K theta. If you know these two equations, it's just we want to know these two equations in this type of meters and all. No need to go for this measurement in deep, no, the construction side and all. We just need the torque equation. We can we can do something with that torque equation, that's why. So see my dears, since under steady state condition, I will rub this. Under steady state condition, TD will be equal to what, my dear? TC, which means half into I square into TL by T theta equal to K theta, or theta proportional to I square. Very, very important relation. Theta proportional to I square. Since theta proportional to I square, the scale of the MI is not uniform. Not linear. The scale is not linear because the theta proportional to I square, the square law is obeying, not linear. There it was simply theta proportional to I, so that the scale will be uniform or constant. Theta proportional to I, right? Y is equal to mx like structure will be there. But now it is not, it is theta proportional to I square. So the scale is not linear. And this MI can be used in both AC and DC. There in MC, moving coil instrument, we can't pass through high frequency AC and all because it won't read. Low frequency, just for frequency measurement we can. Okay, but in MI type instrument we can use both AC and DC. Why? Because theta is directly proportional to I square. So even if for positive half cycle it will be plus I square, even if for negative half cycle again it will be I square. In both the case it will be I square, because minus square means it's again positive. That means the deflection will be in unidirectional. Deflection won't change, so that it can be both used for AC and DC. Both the AC and DC we can use this MI type of instrument. MI type of instrument. Okay, and the sensitivity of Pmmc greater than Mi, and of course torque to weight ratio will be also Pmmc greater than Mi. Sensitivity and torque to weight ratio in both the cases Pmmc will good than that Mi, so that the accuracy also, right? Accuracy also, in case of accuracy also Pmmc greater than Mi. In both the cases, I mean both accuracy, sensitivity and torque to weight ratio, everything, this Pmmc is much better than the Mi type instrument. But the only advantage of Mi is it can be utilized in both AC and DC medias. We can use it in both AC and DC. That is the only advantage. And moving iron instrument errors. MI instrument errors. So first of all there will be hysteresis effect. First of all there will be a hysteresis effect. Hysteresis effect. That means we are passing an AC cycle to the soft iron core. So that what happened, for positive half cycle it is magnetizer in one direction, for negative half cycle it is magnetizer in opposite direction. So definitely if a magnetic material placed in a very magnetic field, of course there will be a hysteresis effect, so that there will be hysteresis loss. We learned in the case of a transformer, right? There will be hysteresis loss. So similar manner here also hysteresis loss. So to reduce this, high permeability magnetic material used, and its name is permalloy. Its name is permalloy. So a material called permalloy is used here in order to reduce the hysteresis error. And next error is that stray magnetic field error. I have already told you that there will be a chance of stray magnetic field because the magnetic field produced in the MI type instrument is very feeble, so that the neighboring circuit magnetic field or the neighboring current magnetic field also affect the reading of the meter. So to reduce this instrument and is what covered with cast iron box. That means, suppose this is our MI type instrument, it can be covered with a cast iron box. This is cast iron box, so that the external magnetic field will not affect. The external magnetic field will not affect the MI instrument. And of course there will be temperature error. For reduce these, we already called a swamping resistor. That resistance is called a swamping resistor, which is nothing but manganese. That manganese resistor is also called a swamping resistor. Is connected in series with the instrument. It's connected in series with the instrument. And of course the error due to aging error, that we can't avoid, right? It will happen. We can't avoid that. It will happen. Okay, is it clear? So that's all about the the MI type instrument. So it can be used in both AC and DC. That point is very, very important. So nothing is more important than that. Okay, and the torque equation you have to remember, theta proportional I square. I told you how to remember. Okay, so that's all about the MI. Okay, write a question, my dear. The deflection of an ideal MI ammeter is 20 degree for 1 ampere DC. If the current of 3 sin omega t to the ammeter flowing, then the deflection will be what? The deflection of an ideal MI ammeter is 20 degree for 1 ampere minus. So we have theta proportional to I square. So in first case theta 1 proportional to 1 square, correct? That is given as 20. So 20 proportional to 1 square, where 1 is the DC, right? DC value. If the current of 3 sin omega t, now this is AC, my dear, this is AC, to the ammeter is flowing, then the deflection will be So let the deflection will be x degree, my dears. So it will be definitely proportional to the current square again, right? But the current will be, what will be the current? It is given as 3 sin omega t. From that, what will be the current, my dear? So it is in the form of I is equal to Im sin omega t. If you take this 3 as the current here, it is maximum value. In first case we used DC value. So in the second case, this is the AC wave. So what is the DC equivalent of AC wave? Which is nothing but the RMS value, correct? It's nothing but the RMS value. So from this, the RMS value will be, IRMS will be Im by root 2. Is it correct? So here also it will be proportional to 3 by root 2 the whole square, where 80-90% of the students will make a mistake. They will directly take 3 square. If that much easy question will not be asked, right? We have to think a little, right? Then only that will be a question for the examination point of view, right? So solve this. Let be equation number 1 and let be equation number 2. It is 20 by x equal to 1 by 3 by 9 by 2, right? 9 by 2. So what will be, my dears? X, 12x will be equal to 20 into 9, or x will be equal to 20 into 9 by 12. If you cut for 3, it is 5. 15 degrees the answer, right? 20 by x is equal to oh, sorry, my dear, sorry. My calculation. Okay. 20 by x will be equal to, this is 1 divided by 9 by 2, correct? 9 by 2. Or when it comes over, 20 by x equal to 2 by 9. Am I correct? 2 by 9. So it will be 20 into 9 by 2 will be x. So it will be 90 degree. Am I correct, my dears? So x will be 90 degree. X will be 90 degree. Okay, so that is the answer. So 90 degree will be the deflection when a current of 3 sin omega t is passing through the coil. Is it clear, my dears? Is it clear? Is there any doubt? Okay. Can we do another problem? Okay. Write down the question. Write another question. A MI produce full scale torque of of 240 micronewton meter with a full scale deflection of 120 degree at a current of 10 ampere. A current of 10 ampere. Okay, the rate of change of self inductance in microhenry per radian will be listen, my dear. A MI produce full scale torque of, so torque is nothing but developing torque, my dear. Full scale torque is a developing torque. TD is equal to 240 micronewton meter. Okay, let be like that, with a full scale deflection of theta equal to 120 degree. Okay, at a current of 10 ampere, so I will be equal to, okay, the rate of change of self inductance in microhenry per radian will be, so at that time what happened, my dears, Mi produces a full scale torque of 240 Newton. That means at this full scale deflection, when it is deflecting to some angle, that is called the steady state condition. So at steady state condition, TD equal to TC. Am I correct? TD equal to TC. So TD, which is nothing but 240. So 240 micronewton meter is equal to what? What is the equation for half I square into TL by d theta symbol? Just we want to find DL by theta, that's all. So it will be 240 micronewton meter into 2 by I square is nothing but 10, so it will be 100. So it will be 2 into 50, so 24 by 5. So what will be 24 by 5? You will get 4.8. 24 by 5 microhenry per radian. Okay, so that is the answer. That is the answer. No need to use of that theta and all. You can directly use TD equation, you will get. TD equation you will get. Is it clear, my dears? Is it clear? Is there any doubt? You can ask. Is there any doubt? You can ask. Okay, so that's all for today. So let's meet again tomorrow with a new session, with a new problem. So until then, bye.